We are the Seoul University Department of Electronic Engineering. Today we are going to introduce our research about single-layer high-K gate oxide field effect transistor. This is a normal force field effect transistor. Here is the metal layer. Here is the isolated layer. Here is the base layer. We know now semiconductor and more small is the industrial goal, and our research is focused on the isolated layer because we found the most transistor, the isolated layer more thinner can make whole transistor smaller. And this is a normal transistor. Here is source, here is drain, and this is our research is basically transistor hafnium, zirconium, oxygen. We found this high-K material can make the isolated layer thinner, so can make the transistor smaller. We found the hafnium, zirconium oxide and the silicon oxide has just 2 nanometers. It's very thinner and more than other material can make now we know the market already operated in 7 nanometer transistor, and now this can more smaller than 7 nano transistor, so this can use in the future. And this material, they have high-K quality. This is a modern material that can have very thinner isolated layer here. This is a molybdenum disulfide, and this is a carbon nanotube. And the carbon nanotube is 1D, and molybdenum disulfide is 2D. And this material can have very small, very narrow, small size. So can make the whole transistor smaller. And this is in the science newspaper. It's now research topic. Or it is possible to make the oxide as thin as 1 atomic layer. What can be learned? Our motivation is not to perfectly criticize oxide film with each atom precisely located in their thermal valence position are available with the technology. Atomic layer deposition. The atomic layer deposition is our technology. And as a consequence, the flow electron in layer box are expected in mimicking the exact behavior of artificial atom. Because artificial atom have a real good behavior like we expect. And in artificial atom, total electron have to obey the rule of real atom, except that the artificial atom have a lower geometrical symmetry of mirror image. So its symmetry is very important. And when n is the electron, and electron number is when we found when electron number is even about 268, and the box will stable, and the environmental balance, electromagnetical interaction, and when the number is 3 or 7 or 9, etc., the box became unstable. Well, when it's R, the electron is R, will turning liquid current will appear. You won't know the detail. Here is the science reporter. We found some material candidate have more thinner than carbon nanotube, have more thinner, small size. The aluminum oxide and the zirconium oxide and the hafnium oxide and the zirconium aluminum oxide. And this kind of material have the best thinner. Here is the detail. When electron in the six number not have every corner have a good pair, and magnetic well balance, and the single electron turning current appear at 7. This means when 6 electron not very stable, and when 7 first electron appear, then this kind of structure will unstable. Then will have liquid current, and when liquid current appear, that's unstable. So only six electron, that's thinner, most thinner size, and a pair of anti-spin electrons are natural form as illustrate. We make experiment to find this function. That this function, this is the voltage, threshold voltage, and the single electron liquid current here, and this is the width of our isolated layer, and this is derived from this function, and this function is our research, and in this paper there have a very famous function that's calculated from Poisson equation. This is famous in Nature, this paper, and when we calculate this root, very equal this sign very famous function. So we know this is right. This talk about isolated layer what, and the isolated area. Isolated area is the most important because the area very narrow and the isolated layer will very thinner and whole transistor will very small, very small. So the ones can calculate from here. Here is our experiment from the material that's already showed in the table. And here's traditional material. This silicon oxygen, this aluminum oxygen, this is the corneal, this is the corneal oxygen, this is titanium. This Socio titanium oxygen. When here is the Morley number. When the number is 8, let's have 1 nanometer. This material is the corneal oxygen and the hafnium oxygen. This material is more thinner than the nanotube because it only have 8 layers. They have 8 layers, and so if only have 1 layer, well smaller than nanotube. The gamma of equation is calculated and normalized to a constant of 1.12 equation, and measure the width to 1 nanometer. That is adjusted to the gate oxide of the corneal oxygen in reference. The smallest width occur in the prescale Socio titanium oxygen that has the highest dielectric constant, and the large width is reach the scale of 1 angstrom. So the Socio titanium oxygen is we found the best material. We theoretical study one silicon-based LVT and show that it is indeed possible to employ a single-layer high dielectric oxide to incorporate with the single-wall carbon nanotube gate electrode and the single-layer molybdenum diversified 2 dimension and conduction to form a new kind of quantum transistor for continuum of more loads. The establishment of artificial atom like a transistor through the correction between gate to channel turning leaky current demonstrates a lot the importance of total periodical and polarized electron number, and N is the electron number in the center oxide. The size precise of the transistor and the gate with the width is calculated to find that high K more than 4075 substrate titanium oxygen has the smallest width, 1 angstrom, to enter into atomic region. further experiment, we now are underway to test, and will have more reporter. And thank you for my classmates. Here is my classmate. They now work in the NDL, the National Narrow Device Laboratory. Thank you for National Narrow Device Laboratory help us. Yeah, thank you.